bring up the second paper. So for the second paper, we have Quan Zhou from Penn State to give us a talk about Tamper analysis for reference monitors. Okay, can start.
All right, thank you. Let me see if this works. Okay. Good afternoon. My name is Quan, and I'm a PhD student from Penn State. Today, I'll be presenting our work of TALISMAN. The concept of reference monitors has been long-standing through the research and industrial realization of computer security. It was first introduced by James Anderson in the 1970s. Concisely speaking, a reference monitor is a set of design requirements on a reference validation mechanism in a certain system, which enforces an access control policy over subjects' ability to perform operations on objects. A reference monitor meeting the security requirements of a system must satisfy three important properties here. First, it must guarantee complete mediation, such that all access control policies are indeed enforced. Next, it must be tamper-proof, in the sense that no incorrect access should be granted by tampering with the input. Finally, it must be small and simple enough to make it formally verifiable. While complete mediation has been intensively studied, there has been few prior work on tamper-proof, let alone the even stronger property of full verifiability. So in this work, we will be focusing on the tamper-proof property. One widely adopted use of reference monitors lies in the Linux operating system, which we call Linux Security Module, or LSM. There are several implementations of LSM, such as SELinux and AppArmor. One example of LSM is checking whether a process P has the permission to write to a file F. The workflow of such checking, as we demonstrate with the figure here, is that the untrusted kernel gathers the information of the corresponding subject process and the object file, sometimes even the operation, and pass them into a hook function of the LSM. The hook function's responsibility is to read these inputs, form an authorization query, and pass the query into the authorization function. Finally, the authorization function will make the decision to granting or denying the permission based on the predefined access control policy. While this workflow seems okay at first glance, there are several ways of breaking the tamper-proof property. For example, in the LSM, the security identities of subject and objects are stored in the kernel or the host program. A malicious kernel may tamper with such data. Also, the request input of a hook function may be incorrectly used during the authorization process. Moreover, carefully crafted input may even completely bypass the authorization function. All of these has been found in current implementations of LSMs. Due to this reality, we believe it is necessary to design a static tamper analysis to detect how hook functions violate the tamper-proof property in constructing authorization queries. Moreover, we need a systematic way to endorse benign violations. Our approach to model reference monitors tamper-proof property as is to model the reference monitor's tamper-proof property as an information flow control problem. There are two major challenges in this approach. The first one is that using standard noninterference as the formalization of the problem reports too many false positives, especially when implicit flows are considered. Second, performing manual endorsement is both impractical and error-prone, which requires us to design a systematic way of endorsement. With the workflow of reference monitors at hand, we formally model the tamper analysis as an information flow problem here. This formalization first defines the integrity lattice of data objects. So each data object originates from a location in the system where the reference monitor managed data has a higher integrity than kernel managed data. Static data has higher integrity than dynamically allocated data. Also, each data object should serve one of the subject, object, or operation purposes in constructing the authorization query. In some cases, multiple purposes can be found in a single data object. We define the source of the information flow as any data flowing into the authorization function, either explicitly or implicitly. On the other hand, the sinks are the arguments passed into the authorization functions. We apply the non-interference property to the information flow problem and form the following requirement. For any two different executions of a hook function call, where only the low integrity sources change, the high integrity sink function calls must stay intact. The so-called intact here demands for two specific properties. The first one is that the parameters passed into a sink function must be the same across executions. And the second property requires that sink function calls must match between different executions. Note this is a requirement on implicit flows. However, it is notoriously known that strict non-interference produces too many false positives. Our integrity model can't escape this problem either. We show here with a simple example how strict non-interference rejects benign LSM code. This is a hook function in the AppArmor implementation of LSM. The AAP trace function at the last line is the identified sink function. Consider the two illustrated execution traces. T1 calls and returns the result of the sink function, whereas T2 ends up returning an error code without calling any sink function. Apparently, this code violates the second rule above and will be rejected. The problem with the second rule is that it restricts the control flow of a hook function to be influenced by the inputs. We understand that it is apparently impossible to avoid this in practice, and we propose two relaxations to mitigate the problem. The first relaxation allows the control flow to deny authorization or returning a non-zero error code without calling any sink function. The code here shows an example of such control flow. The first line of the function body calls a kernel-defined function, and the hook directly denies the authorization request if that fails. We allow this behavior because it's perfectly fine for a request to fail some preliminary checks. And in such cases, no permission will be granted with a denied request. The next relaxation handles cases where inputs affect the sequence of called sink functions. Looking at the code again, we can see that the sink function, AAP trace, is only called in the else branch. This behavior should be allowed in the relaxation because it is common in access control authorization to call different sink functions based on the input parameters, or sometimes even skip some sink function calls. So by introducing the two relaxations to the strict non-interference, we are able to allow benign control flows based on the specifications of the security policy. It is worth noting that these relaxations preserves the integrity requirements of LSMs with the following guarantees. First of all, no untrusted input will be able to bypass all sink function calls and return success with the relaxed control flow restrictions. Moreover, low integrity inputs affecting authorization decision over the same sink function call sequences are indeed captured, same as in the strict non-interference. And if you're interested in the formalization, we provide the full details of relaxed non-interference in the paper. While relaxed non-interference removes the majority of false positives for us, we still need to handle benign true positive violations. Our solution is to systematically endorse certain information flows based on the nature of them. We provide a two-level endorsement strategy starting with static endorsement. Recall that in relaxed noninterference, we allow authorization bypass, which denies the permission request. However, there are also many cases where permission can and should be granted even with authorization bypass. Looking at the code here, if an inode is not in the mediated file system list, it can be granted access by any subject and any operation without the need of further checking. In general, we observe two cases, namely objects that are publicly accessible and subjects with admin privilege. We statically endorse those code patterns which bypass authorization. Next, we go over the second layer of the endorsement, that is dynamically endorsing the untrusted input data from the potentially malicious kernel with integrity check. To make sure there's no tampering of kernel-managed input, we insert two endorsement functions in green there into the process. At the beginning of a hook function, we record the input's security invariants incurring integrity violations. By the time an authorization decision is made, a verify function compares the current value and previously recorded value of data objects. If a discrepancy is found in this process, a tampering must have happened. We implement the dynamic endorsers with a few reusable templates for the ease of use by developers. While the previous endorsements cover most of the cases we found with violations, there are several more complicated scenarios where simple endorsement wouldn't work. Some hook functions invoke multiple authorization checks in a single execution. Moreover, there are data objects that are used for different purposes in those authorization checks. Currently, in order to resolve those cases, extensive ad hoc manual effort is required to justify the underlying reasoning and making sure endorsers are placed correctly. With all the discussion in the technical details, I will now present our evaluation results. We tested the tool on 145 hook functions across 3 different LSMs. The first table here shows the comparison of found violations between the relaxed and strict non-interference in each and all dimensions of the lattice. We can see that with the relaxation, false positives are greatly reduced. The overall false positive reduction rate is around 70%. In both Tomoyo and AppArmor, the reduction rate is even over 90%. This clearly demonstrates that the effectiveness of our relaxed non-interference. Next, we look at a higher level picture of hook function verification. This table shows the hook function count of analyzed, verified after endorsement, and those that still contain flaws even after endorsement. It also breaks down to the root cause of the flaws in 2 cases. Case 1 is authorization bypass returning 0, which cannot be endorsed. And case 2 further breaks down on the intended dimension of the data objects, introducing the violations. The scary fact here is that not a single hook in Tomoyo or AppArmor can be verified after endorsement. And all those flawed hooks are caused by an exploitable vulnerability, which I will introduce in a minute. Before doing that, we further show our investigation of the actual flaws in the remaining hooks. A large number of hooks were written in a bad coding style which returns success on either failed no-pointer check or invalid operations. The LSMs returns success with the assumption that the kernel will handle those cases. We believe that this is a bad communication protocol between the LSM and the kernel, and we strongly advise the system developers to fix them. On the other hand, all hooks in AppArmor and Tomoyo contains the exploitable vulnerability, object lookup vulnerability. The last unknown category refers to the hook functions with complex internal logic introduced earlier. Finally, let's look at the object lookup vulnerability in AppArmor and Tomoyo. We observe a mismatch between the canonicalization in case-insensitive file systems and case-sensitive access control policies. Consider the case in the figure. A request on lowercase full file cannot match a deny rule in the access control policy, which specifies and checks the file name in the uppercase full. Since no deny rule can be found, the LSM incorrectly grants permission on such file. The SELinux implementation uses a different mechanism of tracking pathnames security identities by integer IDs, which saves it of suffering from this vulnerability. So with that, I will wrap up with the summary of our paper. We modeled the tamper-proof property of LSMs as an information flow integrity problem. The vanilla non-interference is too strict with all the implicit flows considered. We relax the non-interference, which solves the problem by removing most false positives in the analysis. And a two-layered endorsement strategy is successfully applied to the benign integrity violations. And lastly, our tool identifies exploitable vulnerabilities in reference monitors. And that's all for my presentation. Thank you for your attention.
All right, thank you. Any questions? Okay, if no, I'll ask some. I guess the first is you only basically performed analysis for the LSM. How hard it is to extend this to, say, the normal DAC authorization checks in Linux? The normal DAC, discretionary access control.
We haven't tested on that yet, but we did actually perform some experimental evaluations on, say, X server, other implementations of reference monitors in some other systems, or yeah. But yeah, I mean that's a good direction for future work.
How hard? What's the main challenge? Just annotation, or?
I believe our methodology is general enough to perform them as long as we are able to identify the sources and the sinks successfully. Yeah. Okay.
All right. I guess the second one is more clarification. So this is done statically, and under the semantic of assume correct execution. Mm-hmm. So no memory error, right?
Can you repeat? Sorry.
So your verification is done using static analysis under normal execution semantic. Mm-hmm. So it doesn't prove basically if there is memory error. The kind of tamper-proof still can be proved, right?
The tamper.
If there is memory corruption, this whole verification goes away, right?
You mean when there is memory corruption?
Yes.
Will there be?
Well, invalidate the verification results, right?
That's a very good point. So we are assuming that all the LSM managed memory is safe. It cannot be corrupted, but apparently that's not true. So we're proposing actually an isolated memory space for the LSM, which is managed correctly. Memory corruption at least won't happen in that scenario.
Okay. All right. So Okay, to, I guess, save some time, let's thank the speaker again, and we can move to the next paper.